Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. We will see some constructions of threshold secret sharing which are very popular, but they are inefficient, and this will be the motivation for our next lecture where our goal will be to design efficient threshold secret sharing schemes. So, just a quick recap, we had seen the construction of additive secret sharing, namely n minus 1 out of n secret sharing, where the threshold was t is equal to n minus 1. And in the last lecture we asked ourselves that how can we design a secret sharing scheme for any given t which is strictly less than n, which is not necessarily n minus 1. So, let us first see a scheme by Benalo et al, which is a very elegant construction. And what is the underlying idea here? The underlying idea is that since we want to design a T out of n secret sharing scheme, and remember T out of n secret sharing scheme means your access structure consists of subsets of size T plus 1 or more. That means your minimal authorized subsets are of cardinality T plus 1. That means if any subset of T plus 1 shareholders make their shares available, the reconstruction algorithm should give you back the secret, whereas unauthorized subsets are of cardinality T or less. So, the idea here is the following: you take any authorized subset B of cardinality T plus 1, and for that specific cardinality, that specific subset B, you run an instance of additive secret sharing, assuming the threshold to be t and n to be t plus 1. Okay. That means you ignore the parties outside the set B and just focus on the subset B, and let the dealer run an instance of additive secret sharing, assuming that it is only the parties in B with whom he wants to share the secret. You do not want to share the secret among the parties outside the B. Now, you might be asking that what about the parties outside the B, if they come with their shares, you are not giving him any shares? Well, they will be part of another candidate subset B of size T plus 1, and for that candidate B an independent instance of additive secret sharing will be run. Okay. So, the idea is dealer does not know in advance that which authorized subset will be coming to reconstruct the secret. It could be either the authorized subset B1 or the authorized subset B2 or the authorized subset B3. It could be any of the possible authorized subset whose cardinality is T plus 1. For each of them, he is basically giving them enough number of shares, so that if they come together they should get back the dealer's secret. That is the underlying idea. Okay. So, let me demonstrate this scheme assuming a concrete value of n and t. So, we take the case where there are 4 parties, and again all the computations here will be performed over a group with respect to n plus operation, and I am taking the case where n is equal to 4 and t is equal to 2. That means, now you can see here I cannot run my earlier additive secret sharing, because the earlier additive secret sharing demands the threshold t to be 3. But here it is given to me that I have to design a scheme in such a way that if any 3 shareholders or more than 3 shareholders make their shares available, the secret should be reconstructed back, but 2 shareholders or less than 2 shareholders, their probability, the probability distribution of their shares should be independent of the underlying secret. That is what is my goal. So, what dealer is going to do here is the following: he has the parties shareholders 1, 2 and 3 and 4. He imagine in his mind various possible authorized subsets. So, remember t is equal to 2. So, the minimal cardinality of any authorized subset will be t 3, t plus 1 3. So, these are the possible authorized subsets from the viewpoint of the dealer. That means, it could be the case that P1, P2, P3 wants to learn the secret. If that is the case, they should be allowed to learn the dealer's secret, or it could be the case that it is P1, P2, P4, or it could be the case that it is P1, P3, P4, or it could be the case that it is P2, P3, P4. Of course, entire collection of parties, that also constitutes an authorized subset, but that is not a minimal authorized subset. We are basically focusing on the minimal authorized subsets. Any superset of them is also trivially an authorized subset. So, now what dealer does is, he thinks in his mind that okay, I want to do a secret sharing only considering party 1, 2 and 3 as the possible shareholders, that is all. We do not bring the fourth shareholder into the picture, and it runs an instance of 2 out of 3 secret sharing, right. So, it runs an instance of 2 out of 3 this. So, this is an instance of 2 out of 3 secret sharing, which is an instance of additive secret sharing, and for that what dealer has to do? Dealer has to choose the first 2 shares uniformly at random, and then it has to compute the third share such that all the 3 shares sum up to the secret S, and then the first share which I am calling as S11, which will be communicated to the first shareholder to the party number 1, the second piece will be given to party number 2, the third piece will be given to party number 3. Independently, it runs another instance of 2 out of 3 secret sharing, assuming that it wants to share the secret only among 1, 2 and 4. That means, it is now not bringing the party number 3 into the picture, and he is assuming that he wants to share the secret only among 1, 2 and 4 in such a way that only when 1, 2 and 4 come together they should get back the dealer's secret, but if either 1 or 2 or if either 2 or 4 or if either 1 or 4 come together, they should fail to get the secret. How can dealer do that? Again, just run an independent instance of 2 out of 3 additive secret sharing, namely pick the first 2 pieces uniformly at random and set the third piece to be such that summation of the 3 pieces should be the dealer's secret, and now give the piece number S21 to the first shareholder in this group, give the piece S22 to the second shareholder in the group, and give the third piece now to the third shareholder in the group, but now the third shareholder is not party number P3, it is actually party number 4. Independently, dealer runs another instance of 2 out of 3 secret sharing, assuming that it wants to share the secret only among 1, 3 and 4 in such a way that only when all the 3 parties P1, P3, P4 come together, the secret should be reconstructed back, but if it is only 1 or 3 or if it is only 3 or 4 or if it is only 1 or 4, they should fail to get back the secret. How dealer can do that? Well, he has to pick the first 2 pieces independently uniformly at random and set the third piece in such a way that the summation of the 3 pieces should be the dealer's secret, right, and now give the corresponding pieces to the respective parties in this short group, and now run another instance of 2 out of 3 secret sharing for the same secret. Remember, dealer's secret in all these independent instances of 2 out of 3 secret sharing is the same, it is the same secret S, right, the secret is not getting changed, right. So, it runs an instance of 2 out of 3 secret sharing for this last group and distribute the corresponding share only within this restricted group. Now, what will be the overall share for party 1, 2, 3 and 4? Because now party 1, 2, 3 and 4 are present in several groups here. The overall share for party P1 which I denote by this capital S1 will be now this whole collection of 3 pieces. Why this whole collection of 3 pieces? Because P1 is given some piece of information with respect to this possible authorized collection, this possible authorized collection and this possible authorized collection, right. In the same way, the shares of all the pieces which are given to party P2 by the dealer, that will be constituted as the overall share for party number P2. In the same way, whatever pieces party P3 has got from the dealer based on which candidate authorized subsets P3 is part of, the collection of all those pieces actually constitutes the overall share for P3. And in the same way, if I consider P4, all the pieces that S4 P4 got as part of various candidate authorized subsets constitute the overall share for the party number P4. Now, let us try to argue the correctness property and privacy property, whether this mechanism achieves the correctness property or not. So, what is the correctness property? We want to ensure that if any subset of 3 parties come together, then can they learn the dealer's secret, 3 or more number of parties. Of course, if 3 can learn, any superset of that can also learn, right. So, imagine if P1, P2, P3 if they come together, will they learn the dealer's secret? Well, if P1, P2, P3 come together, that means we are now talking about this authorized subset, and indeed the shares S11, S12, S13 have the property that if they are added, it gives you back the secret. Or it could be the case that 1, 2 and 4 they want to learn the secret. Can they learn? Yes, the pieces S21, S22, S23 are such that if they are added together, it gives you back the secret. Or if 1, 3 and 4 they want to learn, can they learn? Yes, the pieces S31, S32, S33 they are such that if they are added together, they gives you back the secret. Or if 2, 3, 4 they want to learn, can they learn? Yes, the pieces S41, S42, S43 they are such that when added, it gives you back the dealer's secret. So, the correctness property is satisfied. Now, what about the privacy property? Does it satisfy the privacy requirement? Can I argue that if I take any subset of 2 parties, then the probability distribution of the information that those 2 parties receive from the dealer is independent of the secretess? My claim is that you take any unauthorized subset of T or a small number of shareholders, they will miss at least one value to get back the secret, and that missing value could be any value, and hence it could be any secret which dealer has actually shared with those 2 parties. So, for instance, imagine that I talk about an unauthorized collection consisting of the first party and the second party. What are the pieces that they have got? They have got S11, S21, S31, S12, S22, S41. You might be saying, thinking that okay, that is lot of information to get back secret. No, if 1 and 2, if I think it from the viewpoint of the first instance of the dealer's additive secret sharing, then 1 and 2 they are present in this instance where they are actually treated as part of the share whole bunch of shareholders. They will have S11 and S12, but they do not know what is the S13 that this third party got. Since S13 is kind of not known to P1 and P2, that means based on this instance of secret sharing which dealer has executed, P1 and P2 cannot infer anything about the secretess. Now, 1 and 2 are also member of this instance of the secret sharing, where they learn S21 and S22, and remember S21 and S11 they have no relationship, they are picked independently. I stress they are picked independently. Similarly, S12 and S22 they have no relationship among them, they are picked independently. Now, as part of this second secret sharing instance, can I say that S21 and S22 helps the two parties to learn anything about the secret? No, because this third piece S23 is missing for them, and it could be any group element from the group, and hence it could be, that means S21 and S22 could be the shares corresponding to every candidate S from the group. So, that means this instance is also useless for P1 and P2. Now, what about the third instance? In the third instance P2 is missing, it is only P1, right, who is from the set B. And now, remember S31 has got nothing to do with S11, S12, S21, S22. He is getting it completely independent, because all these 4 instances they are picked, they are executed independently of each other. Now, there are 2 pieces which P1 is lacking here, and hence it cannot learn anything from this third instance as well. Now, let us consider the fourth instance. In the fourth instance, from the set B unauthorized collection, it is only the party number P2 who is present, but there are 2 pieces in that instance which is missing for him, and hence it could be any candidate S for which he has seen the S41. That means, even though it might look like that now the parties in B are getting too much of information, because members of B are present in multiple possible executions of the additive secret sharing instances executed by the dealer, we have cleverly executed the independent instances in such a way that for each instance the parties in subset B will be missing at least one piece of information. And even though they know that all these invocations are with respect to the same secret S, they cannot pinpoint what is that secret S. It could be any element from the group space, from the group, and that is why this constitutes a valid T out of n secret sharing scheme. What is the problem with this secret sharing scheme? Well, the correctness and privacy is satisfied, but what is the share size? The share size for party 1 is actually 3 group elements. The share size for party 2 is 3 group elements. The share size for party 3 is 3 group elements. The share size for party 4 is 3 group elements. This is unlike your n minus 1 out of n secret sharing, additive secret sharing, where the share size was just one group element, right. Share was just one group element, its size was the same as the secret, but now the secret is just one element of the group, but the share size for each shareholder is 3 times the size of the secret. Now, in general, if my threshold T is n by 2, right. So, in this case it was n by 2, but I am talking now about an arbitrary n and arbitrary t, where t is roughly n by 2. Then how many instances of additive secret sharing D has to execute? So, D then has to execute n choose t plus 1 independent instances of t comma t plus 1 additive SS. Why these many? Because these many candidate authorized subsets could be there, minimal sized authorized subsets could be there for the dealer, and for each such possible candidate authorized subset it has to run an independent instance of additive secret sharing. But what is this quantity n choose t plus 1? It is exponentially large if I set my T to be n over 2. That means, the share size for each party will be exponentially large, because each party could be now present in exponentially many candidate authorized subset, and with respect to each candidate authorized subset it will be receiving an independent share as part of the additive secret sharing which dealer would have executed for that candidate authorized subset. And that is why even though this is a valid secret sharing scheme, it becomes impractical if my value of n and t increases, and if my threshold t is roughly half the number of parties. This is unlike your strict n minus 1 out of n additive secret sharing, because there it does not matter how large is your n, each party will just receive a single group element as its overall share, but that is not happening in the scheme by Benalo et al. Now, let us see another interesting T out of n secret sharing scheme by Ito et al, and this also might look similar to the construction of Benalo et al, but it is slightly different. Okay. What is the idea in this scheme? The idea in this scheme is now we will ensure that for every unauthorized subset there should be some piece, some share which is not available with the parties in that unauthorized subset. If we ensure this, then it does not matter what exactly is that unauthorized subset, whether it is the first subset of T shareholders or whether it is the last subset of T shareholders. If I ensure that my sharing algorithm has this property, then the privacy property will be achieved. So, again let me demonstrate it with an example. I take my n to be 4 and t is equal to 2. So, I want a sharing mechanism so that any subset of 3 or more shareholders have enough information to get back the secret, but any subset of 2 or less number of shareholders do not have sufficient information to get back the secret. So, what we do is we focus here on the maximal sized unauthorized subset. So, since t is equal to 2, I am talking about the largest possible unauthorized subsets which can be there. So, I am talking about the case where my unauthorized subsets are of cardinality 2, because any subset of these forbidden sets are also trivially forbidden sets. So, I am basically trying to consider of the worst case scenario, I am trying to consider about the largest pool, largest possible sized unauthorized subsets. So, that is why maximal forbidden subsets, maximal, by maximal I mean here that any subset of these forbidden subsets are also forbidden subsets, they are not allowed to get back the secret. So, I have listed down all possible forbidden sets here. Let us call them as A1, A2, A3, A4, A5, A6. So, how many such maximal forbidden sets you can have? You can have n choose t such subsets, right. Now, I focus on the complementary sets, and when I say complementary, I mean complement with respect to the set of n parties, not with respect to the power set, that is important here, right. So, by complementary I mean here, so this set is basically the difference of the set of n parties and A1. The second complementary set is P minus A2, P minus A3 and so on. Okay. And it is not necessary that complementary set is an authorized set, it may or may not be, right, it depends. So, for instance, in this specific case what is happening is that each complementary set is also of size 2 and each set of size 2 is a potential forbidden set, right. So, in this specific case since the complement is take with respect to just a set of parties and not with respect to the power set of the set of shareholders, I cannot say that the complementary sets are always authorized sets, right. So, what is the idea that we want to follow here? We want to ensure that dealer should have shared its secret in such a way that if the parties in A1 try to get back the secret, there is something which is missing for them, or if the parties in A2 is trying to reconstruct, there should be something which is missing for it, and so on. How the dealer can do that? So, dealer has a group element which it wants to share. It now creates an instance of additive secret sharing in the following way. So, see how many forbidden subsets are here? There are 6 possible forbidden subsets. So, it randomly picks 6 group elements S1 to S6 subject to the condition that their sum is its secret S. So, how he can pick the random S1 to S6? Well, he can first pick S1, S2 up to S5 uniformly at random from the group, and then it can set the 6th piece to be the difference of S and the first summation of first 5 pieces. That means, for the same secret S, the shares S1 to S6 could be any 6 pieces from the group, because he is picking the first 5 pieces uniformly at random. That means, every time dealer wants to share the secret, the shares S1 to S6 will be different with different probability. Now, how he should distribute this S1 to S6? Remember, we have to ensure that this idea is followed. He gives S1 only to the parties in P minus A1, that means to the complementary set with respect to A1. And remember, when I say give, I mean I am assuming here that there is a private channel between dealer and every shareholder. So, this S1 piece is given to this party number 3 over the private channel and party number 4 over the private channel. The piece S2 is given to the complementary set with respect to A2, and like that the piece S6 is given to the complementary set of parties with respect to A6. That is a simple secret sharing mechanism. Okay. Now, we have to argue whether the correctness and the privacy properties are achieved. Before going into that, what will be the overall shares for the individual parties? So, now what will be the overall share for party number P1? Because party number 1 now is going to receive multiple piece of information from the dealer. So, he is going to receive S4, S5 and S6. So, that will be its overall shares. What will be the shares of party number 2? He is part of this complementary set, this complementary set and this complementary set. In the same way, this will be the overall shares of P3. Okay. And this will be the overall shares of S4. Now, here the privacy property is very easy to argue and the correctness is slightly subtle to argue compared to the previous scheme. In the previous scheme, correctness was easy to argue and privacy was subtle. Why the privacy is easy to argue here? So, imagine it is the party 1 and 2 who tries to learn the secret, because they together constitute an unauthorized collection. Will they be able to learn the secret? No, because this idea is followed for them. Because if I consider this unauthorized collection consisting of P1 and P2, there is some piece of information, namely S1, which is not given to the parties P1 and P2, right. And since S1 could have been any value from the group, that means it is any candidate element from the group which dealer could have shared. In the same way, let us consider whether 3 and 4 will be able to learn anything. If, because now you might be saying that okay, 3 and 4 have too much of information, they have S1, S2, S4, S1, S3, S5, will they learn anything about the secret? So, the point here is this parties 3 and 4 constitute this candidate forbidden set, and with respect to this candidate forbidden set, there is some missing information, namely S6, which is not available with both 3 as well as P 4, and S 6 could have been any value from the group, and hence it could have been any value from the secret space which dealer could have shared. So, that is why you can focus on any unauthorized collection of 2 number of shareholders. With respect to them, there is at least one SI which is missing for them, and hence it could be any candidate secret from the group which dealer could have shared. That means, if A 1 is trying to learn, they will fail to find out S 1. If A 2 is trying to learn, they will fail to find out S 2 and so on. On the other hand, the claim here is that you take any authorized subset of T plus 1 or more number of shareholders, they always have all the 6 pieces, okay, to get back the secret. So, for instance, if I consider 1, 2 and 3, will they have all the pieces? Yes, they have S 1, S 2, S 3, S 4, S 5, S 6 all within themselves as a group, because they constitute an authorized subset, and hence they can add them and get back the secret. Or if I focus on say 1, 3 and 4, together they constitute an authorized group, and indeed they have all the 6 pieces and they will be able to get back the secret. How can we argue this for a general N and T based on the construction? Well, you take any authorized collection B. Okay. Can I say that there is at least one party in B who will have S 1? Yes, the answer is yes, because there will be at least one party in the B who is not a member of A 1. That is why B is an authorized collection. B is definitely not a proper subset of A 1. Okay. B is definitely not a proper subset of A 1, because a proper subset of A 1 is also a forbidden set. So, B definitely consists of at least one party who is not in A 1, and that one party will have S 1. In the same way, can I say that the party in B who is an authorized set will have S 2? Yes, my claim is there will be at least one party in the authorized set B who is not a member of A 2, and since it is not a member of A 2, it will have the piece S 2. And I can run the same argument. I can say that you take any AI, okay, with respect to that AI, there will be at least one party who is not in AI, but present in B, and that party will have the missing piece Si, and that is why the parties in B will have all the pieces S 1, S 2, whatever is the number of S pieces, and hence they can get back the secret. Right. So, this is again a very interesting construction of T out of N secret sharing, but again the problem here is that it requires exponential number of shares. Why? Because the number of forbidden sets will be N choose T, right, and that is why if K is equal to N choose T, basically dealer has to distribute or compute K random pieces of shares for its secret S, and it has to distribute, and that requires exponential amount of computation and communication. So, this is the summary of T out of N secret sharing. We have seen two constructions, might look similar, but based on different ideas, and the downside is that both of them require exponential amount of computation, communication and storage. Why computation? Because we have dealer has to compute so many number of shares. Why communication exponential? Because those many number of shares it has to communicate to the respective shareholders. And why exponential amount of storage? Because each party has to store whatever information it is getting from the dealer. So, all these three resources will be exponentially large. So, now the next challenging interesting question is, can we design an efficient, by efficient I mean polynomial time constructions, polynomial time solutions, can I design efficient T out of N secret sharing scheme for any given T less than N, and that will be the focus of next lecture. Thank you.